Okay, good afternoon to everyone on Zoom. If you can hear me, give me a thumbs up, please. Sorry about the delay. We're getting started here in a minute. Thank you, Anthony. Then I have to switch this laptop. Wonder why this is shows there, but it's not showing on the projector. That's weird. Hmm. That's kind of weird. Does anyone know how to get it on there? No, it's usually weird. We never have that issue. Usually just hooks up. Maybe we have to reset the system. Oh, there we go. Good. Okay. Amazing. That's good. Okay, so sorry to everyone on Zoom. We had to make sure that the screen is showing on the projector. It was not. Okay, we can go ahead and begin. So a few course logistics. Currently we're in week 7. We're still in the application layer. We're gonna continue, sorry, the transport layer. We finished the application layer last week. We're gonna continue with the transport layer. And the schedule for the next week is that we're gonna still continue on the transport layer next week. We're gonna talk about TCP, congestion control, more on congestion control. And then the plan is that next week we'll have 2 lectures. The week after we'll have 1 lecture and then a midterm review. And then the midterm is looking like it's going to be on the 20th, on a Monday. It's gonna fall on a Monday where Wednesday we're gonna have a review. There will be no class. It will be intended as a review for you to review the material. And then the Monday is intended for your midterm, and that's gonna be all day. So I'll release what the midterm will look like, what questions might be on there from which chapters, but it's gonna be primarily from chapter 1, the application layer and the transport layer that we're focusing on now. So that is it. Does anyone have any questions before we begin? Okay, that's good. So the programming assignment, I received a couple of questions that could be useful to share with you guys, is that the programming assignment must be done using the TCP protocol, because the UDP protocol is really easy, but we use the TCP, that gets you the combo of understanding both. So it must be done using TCP. Yeah, and then one of the indicators says if you write 0/0, that means the program ends. And we know that with TCP, it's persistent, so that we need to, as a user, we need to close out the connection ourselves. So that's an indicator for you that it should be TCP. But for those who aren't sure, then it has to be done with TCP. So we can go ahead and start. Okay. So as usual, the slides are derived, a good portion of the slides are derived from the book, and the class is being recorded, so you can refer back to that. So where are we currently in the transport layer? So right now, we started the transport layer itself, and we have talked about the services it provides. We talked about multiplexing and demultiplexing. We talked about UDP. And now we're getting into the principle of reliable data transfer. So that is the idea that we want. So we actually, I have a recap of it here. So currently where we are is we're trying to manage how to transfer data in an efficient manner, and where congestion cannot happen, where data or packets cannot be lost, and where the package itself or the data comes in a specific order. So the first thing that we explored as a protocol to help us transfer that to transfer the data over is UDP. And we said UDP is very quick, it is very efficient, very light, and it comes to the idea comparing it to TCP. There is no handshake, it's connectionless. It just pushes out data and doesn't really care if it gets lost or if it doesn't get received to the client, or the server doesn't receive it. So that is the idea. So we said in the OSI model, or the model that we're looking at, we are as the application, we start with the application. This is basically us working on the application. We make a request, and that is usually a process. This process is going to get attached to the socket. When it gets to the transport layer, and makes a segment using UDP. And we talked about the several header details of the segment itself. Then it goes to the network IP that uses the IP address to deliver the data over to the client or the server. And obviously we have our link and physical media, whether it's wireless or physical transmission link like fiber optic or copper, it would transfer it over to the other side. So that is the general idea. And then on the other side, the network IP or the network layer of the receiver would interpret the data over. So we go to the transport, and we said with the UDP, there's a checksum to make sure that the integrity of the data. It is not the best way of integrity, because we know that there could be a flaw with the bits that get flipped, but it's some sort of integrity. And after it verifies the checksum, even if there's a flaw and it passes it, it delivers it to the application. But obviously, this is not what we hope to achieve. Or we know that with UDP, there's several cases for UDP that works best for us, like video or video games. But when we're working with data that needs to be sent in a nice fashion and in an ordered fashion, integrity of the data matters, the reliability matter. We must come up with something that is better. So we have to start looking at TCP. So the limitations of UDP that we talked about is connectionless. There is no handshake or setup whatsoever. It's the best effort. Segments could be lost, duplicated, or reordered. It is small header compared to the header of TCP, and it's very simple to implement. We have the error detection that we spoke about with the checksum, but we said it is a limited protection. So the limitations of it is there's no reliability, so the loss is not recovered. There's no congestion control. There could be a congestion with the packets that are getting sent. Out of order, packets can be sent and out of order, so there is not that feature is not available with UDP. And applications that are sending reliably must build it themselves. So the applications themselves have to make sure that our goal or the objective is that we, when it comes to the regard of working with the data, we need to make sure either we're using UDP or TCP. So that is that. So lastly, in the last lecture where we stayed at, we talked about UDP, its limitations, and then we got to the idea of how we can build a reliable channel that we can send data on. And we came to a solution of using FSM, so finite state machines. You guys are familiar with the concept, right? Yeah. So it is a way for us to make sure that the data is sent in an order, and there's an abstraction, and we have a state for each phase of the data that is getting sent. So we're going to see how this works exactly. So we have our first state. So this is meaning that the system in some sort of state, either a sender or a receiver. And the state represents like the current condition in the protocol. If we are a sender or receiver, what is our current condition? Are we waiting for data? Are we sending data? What is going on exactly? And then obviously we would have an event that would cause the transition in the state. So this event would be like data is being sent, message is expiring, or message has been received, or an acknowledgement is sent or an acknowledgement is received. So that is the idea. There is some sort of event that is happening where it causes the transition, the state to transition to something else. And the action is when the protocol takes action. That's like even like delivering a packet or sending data down. So that would be the action that would make the transition of the state takes a new place. And then here we have transition two, which is state two. This is the next stage of the protocol. So when we have a sender and receiver, they're going to have both two states. There needs to be some sort of communication between them such that we can make sure that data is being sent, data is being acknowledged. There's a reply from both sides, and so that we have some sort of order. So, and we talked about the analogy of FSM, like finite state machines, is like the lights that we talked about, like the light switch. So it's either on or off. That is the state that we're in. Flipping the switch is the event, and the action would be turning on the light. So if the light gets turned on, that is the action. So FSMs is the idea that gives us a way for us to behave in a matter for both the receiver and the sender. And here's what we want to build. We want to build a reliable data channel between all the receiver and the sender. So this is our goal. The way that the module is structured, we're not diving directly to TCP. We can just go directly to TCP and see how TCP works. But it's trying to get you to think of that. We started with UDP. We know it's connectionless and it has flaws. How can we think of as a point of view of a problem solver? How can we work on each step of the limitation of UDP and have a solution for it? So that's how we're going to work today. So here's the process of how it's going to be. We have the abstraction of RDT send. We have only a client and a server that is happening, and data is getting delivered on both ends. And we must have a reliable channel in between that can deliver the data and reliably, right? So the first state or the first event that would take place is that we have the sender, and they would say, hey, there's some data that needs to be passed by to the other side. Here's that. And then we have another state, which is UDT send. This is where it prepares the data, makes it as a segment and pushes the packet down to a reliable channel. So currently we're dealing with an unreliable channel. We need to make it more reliable, and we're going to see how that happens. Then we have another state, RDT receive. This is where the packet gets received on the receiver side. And then we have the deliver data, and this is basically to hand the data to the receiving application or to the server in the essence. So these are the four abstractions or four states that would take place, or the events that would happen. And obviously we need to make sure that communication is bidirectional, so both sides can communicate with each other. So that is one idea of building a reliable building a reliable data transfer or data reliability protocol. And then we need data also flowing from both sides, meaning that is bidirectional as well. And we need packets flowing from both sides as well. So that is the idea that we want to make sure. We want to make sure that we send data and packets in a bidirectional way from the client and the server. We want to make sure that data comes in order. It doesn't get lost. It does not get congested. And we need to have backup plan, whether if there's congestion to happen or if there's loss, how can we recover from that? So we talked about RDT1. This is where we assume the channel is perfect. There's no bit errors or no packet loss, so everything arrives in order. But obviously, when it comes to the real idea, we're not dealing with that. So it wants you to make sure, it wants you to understand what we are hoping to achieve and how we are going to achieve it. So we don't have to worry about corruption and loss in RDT 1.0. And here is just a design methodology for you to understand. It's not actually something that is available for us to do. So when it says RDT 1.0, it's not an actual protocol that you can go and use. So it's just for us to reach TCP. And we said that we will use the FSMs for sender and receiver. And we said that the sender would send data to underlying channel and the receiver would receive that data from the sender. And we said that we use FSMs, different finite state machines for the sender and receiver. So the sender here in the essence would just wait for the application. The application would say, hey, here's some data for you to deliver. So it is currently in a waiting status. And then obviously we have our receiver as well that is also waiting for data. So on the sender side here, we're looking at the protocol is very simple. So a single state is waiting for a call and above, and then an event would happen, which is the abstraction of RDT send. This is basically saying, here's some data for you to pass down. And then we have the receiver is also is waiting, and it would also get a state saying that RDT RCD, which is it's receiving a packet. So that is that. And this is it. This is an easy process. This is RDT 1.0. We say there is no flaws. There could no problems could happen whatsoever. But we know the network itself is not reliable. So there is going to be flaws that would happen. So that's RDT 1.0. We're going to talk about 2.0, 2.1, and then we're going to go to 3.0 till we get to TCP. So what is some of the limitations with RDT 1.0? It assumes everything is perfect. It assumes that there's no bit errors, no packet loss. The sender just sends, the receiver just delivers. So it is a simple baseline for us to introduce the reliable transfer concept. The limitations is that it's unrealistic because we said real networks are unreliable. And we said that you cannot detect or recover from any errors. So we want to see how we can progress from this current stage. This is what we talked about as RDT 2.0, because RDT 1.0 assumes that the channel is perfect, but that's not realistic. So in the channel, there might be flipped bits. The message could get corrupted or unreadable. So how do we recover from the errors? So before we think about specific protocols that would help us recover from that or find a way to recover from these errors, is to give you an analogy from outside. The scope of this is like when you're talking with someone and on the phone, and then they say something to you or you say something to them, and then the way they acknowledge what you said is they say, hey, I didn't hear you, can you repeat that? Sorry, what was that? And then you would give them an acknowledgement saying that, oh, this is what I said. And then they said, oh, okay, that's fine. So this is what we kind of need. We need a protocol that has acknowledgements. So this is what RDT 2.0 is going to do for us. So in RDT 2.0, we assume that there might be flipped bits in the packets. So to handle, we use the checksum, so the receiver can detect whether errors are taking place. But detecting isn't enough, so we need a way to recover. If there is an error, how can we recover from it? And this is the idea of acknowledgements that we're going to introduce. Just basically saying, hey, I have understood or I have received your message. And we also have negative acknowledgements. So that means that something was wrong with the packet. If there's a negative acknowledgement, that means there's something going on. It either needs to be resent, either needs to be recovered, or something must take place because we want to make sure that packets get in order. And we have retransmission. So usually when the packet, we receive a negative acknowledgement for it, we must make sure that we retransmit that packet. Because imagine you're sending a message to your friend on text messages or WhatsApp, and you send a message and it is not being sent. You want that message to be resent. So this is the idea. We receive a negative acknowledgement and then we retransmit the packet again. But we also, when we resend the packet, we want to make sure it goes in the order that it was sent. So there will be a detailed example that shows that. And then also the RDT 2.0 implements stop and wait. So it uses a stop and wait approach. So the sender transmits one packet and then it stops and stops for an acknowledgement back from the receiver before it moves to the second packet. So that is the simple but effective way to handle bit errors. So we want to send a message and the second packet would not be accepted until the first message is out and sent. So transition to RDT 2.0. We transition from 1 to 2.0. And the solution is that we are adding checksum and plus feedbacks. And we are adding a stop and wait approach. So sender transmits and wait for the receiver response. So far what we have done is we talked about UDP. It is unreliable, the best effort. We talked about RDT 1.0. It's perfect reliability, but it's unrealistic. And we are going to now talk about RDT 2.0 that handles bit errors with acknowledgements and negative acknowledgements. So the FSM is going to be usually carried on with us as we go. It's not going to something that's going to, we're not going to come up with an approach that would neglect that the use of it. So here's what we're going on. We have the sender, and there's going to be two states in the sender. We have wait for a call from above, and that is usually waiting for data from the application. And we have wait for an acknowledgement or negative acknowledgement. So that is waiting for a response from the receiver. So these are the current two states in the sender that we have. Is that clear? Okay, that's good. So when data arrives from the application and is going to arrive through RDT send, the sender would make a packet or would attach a checksum and send it out with UDT send. UDT send is the abstraction or the action that you take to send the data over. When we send the data, we have to wait for a response. So if the sender is waiting for an acknowledgement or a negative acknowledgement and it receives an acknowledgement, meaning that, hey, has been sent and received, then it goes back to waiting. That means the packet was delivered successfully. But there are some cases where we receive a negative acknowledgement. So what we make sure is that we resend the data or resend the packet again, and then we reloop back to the same position because we need to resend the packet and also wait for another response, another acknowledgement for us to go back to the waiting phase. Okay, so that is from the sender. Is that understandable? It's clear. Okay, so we have two states with the sender. We are waiting for data to come from the application. We send the data over and we need to make sure that it has been received successfully. So if we receive a thumbs up or acknowledgement, we go back to the waiting stage. If we receive a negative, then we resend it and also wait for another signal back from the receiver, and then we go back to the waiting stage. So that's how it happened. Now we're gonna go to the receiver side, and it only has one main state. So it is only waiting for a call from above, meaning that it's just waiting for packets to arrive in the receiver side. So if the packet that is received is corrupt, the sender would say, hey, the receiver would send a reply back to the sender and say, hey, it's a negative acknowledgement. There's some sort of corruption that is happening. But if the packet is not corrupt, then the receiver would extract the data, deliver to the application, and send it back to the sender. So the sender, here's the takeaway with 2.0 with what we added. It sends one packet at a time and waits for an acknowledgement or negative acknowledgement. Either waits for a success or resend. The receiver says, hey, if the packet is corrupt, we send a negative acknowledgement. If it's correct, we deliver the data and send also an acknowledgement. Does that make sense so far? Okay, that's good. So now we want to look at how it works when there are no bit errors. So there's no bit errors whatsoever with the packet or the data that we are sending. So here we have both sender and receiver. They're starting at their initial phase. Sender is waiting for data to be sent from the application. The receiver is waiting for packet to be sent from the sender. So the application gives data to the sender. The sender makes a packet with the checksum. And we talked about how the checksum happens last time, where we flip the bits and we carry that wrap around, and then we take the checksum for it. And then the sender would send the packet to the receiver. That's how it would be. And the receiver would get the packet, and we are here taking the assumption that there is no negative acknowledgement. It's a successful acknowledgement. So since it's not corrupted, the receiver would extract the data from the application, and then finally it would send an acknowledgement back to the sender saying, hey, everything is good. And the sender would go back to the state of waiting for data to be sent. So that is, the last slide was, there is no corruption and there is no negative acknowledgements. So that is an awesome phase that we can have. But obviously, we need to test every possible case and see how we can develop that last final protocol that is equipped with all these, you can say, defend mechanisms or all these characteristics that would fight these what if questions. What if the data is corrupted, or what if it receives and not in order? So here's a corrupted packet scenario. Same thing is going on. Sender and receiver are both waiting for a call from above. The application would pass data to the sender, and the sender would make a segment. And then the packet is being sent to the receiver. The sender moves from a wait for acknowledgement or a negative acknowledgement. So it moves to that state, as we said. So now this time, the receiver would send back a negative acknowledgement saying, hey, there is some sort of corruption with that. And it sends a message back saying, hey, it's a negative acknowledgement. Please retransmit the data again one more time. So the retransmitted packet would be resent, and we have to send it back to the receiver. So we make sure we send it back. And then this time it's not corrupt. So the receiver would extract the data, and then also would send a successful acknowledgement back to the receiver, or to the sender, sorry. Does that make sense? Is there any confusion so far? I hope it's very clear. Like it's if we look at the TCP from a high level idea, it makes very sense to us, but we are going into the underlying details. We're basically just working with like, hey, if something happens, how can we fix it? So that is the idea that we're working with here. So we've seen how RD2 2.0 how it works, but it has a flaw. And the fatal flaw that it has is that what if the positive or negative acknowledgement itself gets corrupted? Like what if the sender does not actually know what's happening? Like it does not receive a reply back. So the sender would send everything blindly, and it might not know that it has been received successfully. So it would go back and resend it again. We would have a duplicate packet. So we need to make sure that doesn't happen as well. We don't send any duplicate packets. So we're here looking at the acknowledgements itself. What if that gets corrupted? So this is what we're looking at now. So how do we fix the idea of duplicates or duplicates packets? So in order to fix that, we are going to add a sequence number. And we're going to add a sequence number to every packet. So if the receiver gets a duplicate with the same sequence, then it would discard it. So that is the idea that we're working with. So that way the application only gets one clean copy of each packet. That's why we're moving to RDT 2.1. And also it would have the stop and wait is going to carry on with us. It's not going to go away. We need to send a packet and we need to wait for a reply from the receiver. If we don't wait for a reply, then there is nothing that can make sure that we send the packet correctly. So that is crucial. So now we have talked about so far UDP, RDT 1.0, which thinks that everything is successful. We talked about 2.0. It handles for us the negative, it handles for us the acknowledgement. It handles for us the stop and wait approach. It talks about corrupted packets, and it talks about flipped bits. Now we're looking at 2.1, where it talks about what if the acknowledgements themselves are going to be corrupted. So RDT 2.1, we said we are going to attach a sequence number to every packet. So here we're going to have 4 states instead of 2. So the top 2 is going to handle packets with sequence 0, and the bottom are going to handle packets with sequence 1. So let's go clockwise around the states, starting with there's a no error case. This is making sure that everything is successful. Hopefully the transitions that we have highlights the idea to you as we go through. So obviously we start at 0 from above. Same idea would happen. The sender gets data from the application and it makes a packet with sequence number 0 and it sends it. Then it also waits for an acknowledgement, a positive or a negative acknowledgement. If an uncorrupted acknowledgement arrives, and this time it's an uncorrupted acknowledgement, not an uncorrupted packet. So if there's an uncorrupted acknowledgement, the sender moves to wait for call from above. So the packet it will have a sequence of 1. So then data arrives from the app. The sender makes a packet. The sender would make a packet with a sequence number 1 and then sends it, because we sent it initially with sequence 0, but there's a corrupted acknowledgement, so the sequence would change to 1. So if an acknowledgement for the packet arrives correctly, the sender would transition to, hey, go back to the same stage or the initial stage of wait for a call from 0 and above. So we need to make sure we look at if there's going to be errors, an error scenario. So the phase that the sender sends the data is in waiting for a negative or positive acknowledgement. They're either going to get an acknowledgement or a negative acknowledgement. So it would send the last packet with sequence 0. And similarly, if the sender is waiting for an acknowledgement 1 in sequence 1 for a negative or positive, it would resend the packet with sequence number 1. So the same idea we've seen in the last couple of slides. This time we're just attaching a sequence number. Does that make sense before we move on? Because the complexity only gets harder as we progress. So that's why I want to make sure it's understood. So we looked at the sender and the last slide. Now we're going to look at the receiver. The receiver would only have, initially we only had 1 state. Now we're going to add 2 states for it. It is going to be wait for 0 from below and wait for 1 from below. It's either expecting a sequence 0 or a sequence 1. And we know why there would be a sequence 1 or 0 from the sender side. So if we're waiting for sequence 0 and we receive a non-corrupt sequence 0 packet, we extract the data, deliver it to the app, and we send a positive acknowledgement, and we wait for 1. Here's a mirror case for the other sequence. If sequence 1 gets a non-corrupt sequence 1 packet, it would extract it, deliver it, and send an acknowledgement, then it would move back to 0. So these are just 2 positive packets that are getting sent using 2 different sequence numbers, and they are getting positive acknowledgements. Now, if we are waiting for sequence one and the packet is corrupt, we would send a negative acknowledgement and we would stay and wait for in the sequence one. So if we are waiting in sequence one and sequence zero packet arrives, it's like it could be a duplicate or alt. We would send an acknowledgement saying, hey, do not deliver this. We would stay receiving for one. So if we're in the one phase and we receive a packet being sent from sequence zero, we would not accept it. We would send a negative acknowledgement until we get the correct packet or the correct sequence of a packet. And the same thing would happen for wait zero. If there's a corrupt packet, we would send a negative acknowledgement and we would stay in sequence zero. If an inspected one comes and we are waiting for sequence zero, we would send a negative acknowledgement saying, hey, we are waiting for zero. And currently we're not accepting any packets from sequence one. So that is the idea that we have. So RDT 2.1, a little bit of discussion about it now, is that we know a sequence number is now added to every packet. And there's only two numbers, it's either 0 or 1. And then the wait time, stop and wait is also implemented here. And then we know that the sender must check if an incoming acknowledgement or negative acknowledgement is corrupted itself. And then we see that if it has a sequence 0, then we wait for sequence 0 to be resent. Or if it's corrupted in sequence 1, we would stay in sequence 1 until we have a positive. So we cannot switch from 0 to 1 until the packet is actually sent successfully. On the receiver side, the receiver must check if an incoming packet is duplicates. So it uses the state that it's in to know whether it's expecting 0 or 1. So if we're at sequence 0, we would wait in sequence 0. We would not go to 1 unless we send a positive acknowledgement. So the receiver itself cannot actually know if the last acknowledgement or negative acknowledgement was sent or it was received to the server. So that's why the sequence number itself is important. That's why we have added sequence numbers to our reliable data transferring or the reliable data protocol. Now we move on to RDT 3.0. So we want to handle packet loss. So what if packets get lost in addition to corruption? We looked at the factor of corruption, and we know that with acknowledgements, with wait and approach, and with sequence number, we can deal with corruption. But now we want to see how we can look at the idea of solving packet losses. And we know that when we talked about a little bit in the introduction of the course, packets can be lost or dropped. What if the buffer is too big? Packets can be dropped and there would be a buffer overflow. So we already have checksums, we have sequence numbers, we have acknowledgements, and we have retransmissions. This is what we have so far to deal with. But these four characteristics are not enough to handle the packet loss. So we need something to add a packet loss. So just to give you a human analogy is that if you say something, we want to understand how would we work with that from a human analogy perspective. So if you say something and get no response, what we would do is you would wait a little bit and you would repeat yourself again in a time fashion. So that is the idea of RDT 3.0. We're going to add timeouts and we already have retransmissions. So we're just going to add timeouts to our of the reliable channel that we are working with. So the solution for loss is we're gonna add, hey, wait a reasonable time. Wait a reasonable time for an acknowledgement. If there is no acknowledgement that is received within this reasonable time, retransmit the packet. And when we retransmit the packets, we will not have an issue of out of order because we have the sequence numbers. So what if the packet or acknowledgement was delayed? Like what if it's not lost? Because there could be a delay. So the retransmission would create a duplicate. But we know that with sequence numbers, we would be able to tackle duplicates. Because the receiver would use the sequence numbers to make sure that the packet is in the current sequence number and being sent back with a positive acknowledgement in the same sequence number. It would not switch sequences unless we are sending it in a right manner. So that is why we have a countdown timer and at the sender. So this would be triggered after waiting for a period of time. And the trigger would be that, hey, we resend the packets. So the timeout is the key addition or the improvement or the new feature in RDT 3.0. So we know that the sender now still has four states, just like RDT 2.1. We have wait for call 0 from above. That is waiting for data to be sent. We have wait for an acknowledgement, and we have the sequence number 0 and 1. And the same states are getting repeated in each sequence. So in the way that if we have no error case, the cycle would repeat between just these four states, just as before. Now we want to see what is the improvement with RDT 3.0. Yep, that is the sender with, this is the sender with sequence 0, and this is the sender with sequence 1. And now we want to look at what RDT adds to our improvement. So when the sender sends a packet, it would start a timer as well. And we can see that in yellow, starts a timer. When the correct acknowledgement or a positive acknowledgement it would received, the sender would stop the timer and move on. If the timer expires, then the sender would retransmit, allowing the recovery from lost packets as well as corrupted one. So does everyone get the idea of RDT 3.0 with the timeouts from the sender perspective? Okay, that's good. So now we want to look at still RDT 3.0 with the sender. And we want to look exactly in a detailed scenario with a specific situation where we are waiting for an acknowledgement. So we have not received an acknowledgement yet. So we are supposing that the sender with sequence 0 is waiting for an acknowledgement. That means there is no acknowledgement that arrived in time. And the timer runs out. The sender would say, hey, resend sequence 0 and restart the timer. If the corrupted packet arrives in this state, the sender would just ignore it. We need to make sure we are sending the correct sequence for that specific packet. We cannot jump to the next packet and say, hey, to resend it. We want to send it. We want to send the first one that we had, that we received a negative acknowledgement first, and then we can go to the next packet. When we receive an acknowledgement here that the sender is receiving, or the receiver has sent the acknowledgement to the sender, it would wait from, it would jump to the next sequence. So it would wait, we're in sequence 0, we are waiting. We received the positive acknowledgement. We jump to sequence 1, waiting for a call. But we saw that there is, the timer runs out, we would do retransmission. If we receive a new packet that is corrupted, we neglect it or we ignore it. We send what we have until we get a positive acknowledgement, then we would go to sequence 1. So now when a data arrives from the application, it uses sequence 1 and it starts the timer as well. And it would, this time we're assuming the packet is successful. and we go to wait for acknowledgement one. While we wait in acknowledgement one, the same idea happens here. There's going to be a timeout. To resend sequence one, we would restart the timer. If we get a corrupted packet, we would ignore it, and the acknowledgement is ignored if it's a duplicate. And here that we would go back to sequence 0 when we receive the positive acknowledgement. So does that make sense so far? Everything is straightforward? Okay, that's good. So we're going to look at two cases here. We're going to look at RDT 3.0 in action. So we're going to look at A, where there's no loss. And then we're going to look at B, when there is packet loss. And we have a sender and receiver, and sender and receiver on both sides, okay? So let's look at A first, where there is no loss. This is the perfect case for us. The sender would send packet 0. This is PKT 0. This is just like the first packet. And then the receiver gets packet 0 and replies with acknowledgement 0. So the sender would receive a positive acknowledgement. After it receives that positive acknowledgement, then it would say, hey, I'm ready to send the next packet. So in this time, the sender would send packet 1 back to the receiver, and then the receiver would send packet 1 acknowledgement, and then it keeps going around. Does everyone understand that for the no loss with RDT in action? We have a sender that starts with packet 0. It sends it to the receiver will reply because it's a handshake. So it receives a positive acknowledgement, then it can go to the next packet. We send the next packet over, we can another acknowledgement, and we would move on to the next packet. So that would be the case of there's no loss. So let's look at the packet loss and see how we can deal with this. So obviously sender sends packet 0, receiver gets it and replies with acknowledgement 0. And then the sender this time receives the acknowledgement and it wants to send the next packet over. But here the next packet is lost in the channel. So the receiver never gets it. So it is just waiting. And the sender is also waiting for an acknowledgement, but it never comes from the receiver. So eventually what will happen is that the timer that we have set will expire, and the sender would say, hey, I've waited enough. It's time to resend that same packet. Mind you, we don't go to packet 2. We're still at packet 1. We incorporate the timeout. When that timeout gets triggered, we resend the packet. If a new packet arrives, for the sender, it would just ignore it. We would just stay at packet 1 because we want to send packets in order. So after the time is done, we resend the same packet again, and we get that positive acknowledgement, and then everything would continue as normal as if we had no loss. So this is how RDT would recover with packet loss using timeouts. Does it make sense? Okay, that is good. So in the last slide, we covered if there's a message that is going from a sender to a receiver and that is lost. We have to also keep in mind that the channel can lose messages in either directions. So let's take a look at and see when acknowledgements are lost. So not only when we send data, the message gets lost. It could be the acknowledgements themselves that get lost. So we're going to look at an example where acknowledge lost. And we're going to look at a premature timeout / delayed acknowledgement on the other side. So as usual, let's focus on A. We have a sender and receiver. And just let it finish real quick. So everything is going smoothly until the receiver sends an acknowledgement, but the acknowledgement is lost. So this sent back from the receiver to the sender, it sends an acknowledgement, but this time it is lost. So the sender is waiting. It doesn't know what's happened. And the receiver already got packet 1 and is waiting for the next packet. So nothing moves forward. Here, the same idea applies. we have a timer. The timer would expire. We would go back and retransmit packet one. The receiver would get it and say, hey, it is a duplicate this time. So it does not deliver the data again. Instead, the receiver would just send acknowledgement back to the sender. So that is the idea. So the sender receives it and moves it forward as normal. Does that make sense? Okay, that's good. Okay, now we move to the premature timeout or slash delayed acknowledgements. Everything usually starts correctly. That's kind of like everything in what we do or in life. Everything kind of starts good, but then we have some interference and then we have to recover from that. Okay, but the same idea here is that everything starts correctly. The sender sends packet one, receiver sends acknowledgement one. I'm saying one here, packet one, but packet one is actually it starts with the increments of zero. So zero is packet one and packet one is packet two. Does that make sense? Okay, that's good. So here the delay is being, the acknowledgement is being delayed. So before acknowledgement one arrives, the sender expires. So expires too early. So the sender would retransmits packet one. The receiver would see packet one again and detect it's a duplicate. So it would just ignore the data and just send acknowledgement one. So eventually the original acknowledgement arrives at the sender. This matches what the sender was waiting for. So it sends packet zero next and the cycle continues. And one last detail here, if the sender is waiting for an acknowledgement, but instead receives a duplicate acknowledgement, the FSM just says to simply ignore it. Okay? Does that is clear as well? Okay, that is good. So we obviously performance is a metric or is something that is involved in what we do as network, and we know time is important. So we want to look at the performance of RDT3 under the stop and wait. So we have added the stop and wait approach, and we want to see what is the utilization. So we define the U as the sender, and we want to look at the utilization, which is the fraction of the time the sender is actually busy transmitting data. So we have an example here. We have the link, the transmission link delivers at a rate of 1 gigabits per second. There's a delay, a 15 millisecond propagation delay, and the packet size is 8,000 bits. So we simply apply the formula that we have. The D would be the length of the packet over the rate. And the rate here we have is the bits slash second. So here we see that the time to transmit the packet into the channel, it was only taken 8 microseconds to push the packet on to the link. So stop and wait means like the sender can only send one packet at a time. So we must wait for an acknowledgement before sending the next one. So here the idea is that if we have a high speed link with a long propagation delay, this becomes like a really big problem for us. Because even the link can send data very quickly, the sender is mostly idle. That is waiting for an acknowledgement most of the time. So for the utilization it's currently very low. The sender is busy for only a tiny fraction of time, and the receiver is handling most of the work. The sender is very efficient and very quick. So the utilization here is very low. So this highlights like how the stop and wait is becoming inefficient for us with modern bandwidth or with modern network. There's a long delay in networks that is happening. So we also need to fix the utilization with the stop and wait approach that we have. So we're going to take a look at the same numbers that we have introduced, and we want to compute the sender utilization stop and wait. We want to figure out what fraction of the time the sender is busy versus just waiting. So we want to see both sides of the sender, where it's busy sending and just waiting. So the formula is going to be the sender is going to be here. The L is going to be the packet size in bits. The rate is going to be the link rate, 1 gigabits per second. The RTT is like the round trip propagation delay. So that is 15 seconds each way because we are sending and receiving. The first example we've seen is just for sending. So we do the calculation. So the total time per cycle is the RTT plus the length over the rates. So that means sending the packet plus waiting for the acknowledgement to come back. Because we in the last slide we have the propagation delay, which is 15 seconds. But this time we're looking at the sender and receiver. Yeah, exactly. So we have a utilization. If we plug it all in, we have a utilization of 0.0027. So the sender is busy almost never. The stop and wait really underutilizes the channel. So the limitation comes from the protocol that we have, the stop and wait, which is wasting a lot of time or the available bandwidth that we do have. So in the last slide, we've seen how the stop and wait approach, it is really good for us in terms of like packet loss, packet corruption, and for retransmission. But when it comes to the idea of bandwidth, it is not really so good. So the channel is very fast, but the sender is mostly idle. So we want to see and explore how we can make the channel more efficient. And the idea with that comes is we do pipelining, and instead of sending a data packet to the receiver and waiting for an acknowledgement, what we would do is we would do a pipeline approach. So instead of sending one packet at a time, as we said, the sender would allow multiple packets to be sent, kind of like in flight before we receive their acknowledgements. So not only we send one packet, we send multiple packets, but there's an order for them that has to be done. So, but remember, this requires two main things. This is going to require us to have a larger range of sequence numbers to keep track of all the outstanding packets. And obviously, we're going to need an extra buffering at the sender or receiver to hold the N acknowledged packets that are in line or in flight. Okay. So this diagram we see here, the blue and the green packets in the blue are going, and acknowledgements are coming back in green. Okay. So it's just like kind of like an analogy outside. It's like kind of an assembly line. Multiple products. These are packets. They're moving at once instead of one time. This keeps the channel busy, and instead of waiting for every single packet. Okay. So with pipelining, we know that multiple packets can be sent, meaning that there is an order, but multiple packets can be sent and they're going to be in flight. So here, while the first packet is traveling, we can send the second and third. And let's apply the utilization formula that we have and see how that changes. Obviously here, the utilization formula now is going to be 3L over R because we are sending 3 packets. And if we do the utilization, we have the runtime trip over the length of the packets over the rate. We would see the utilization would increase by a factor of 3. So the main idea is that more packets in the pipeline is more efficient and used for the channel. And that is just like understandable for us as human beings. So it's very, I think before this protocol got developed, if you sit with someone, it's so easy to tell them, hey, this is what we need to do. Really, like, it's very simple. But the development, the back end development of that is very interesting. Yeah, so the utilization increases by 3. So it only We are only adding more stuff is like, I think as you students are saying, when are we gonna stop? When are we gonna reach a time where we don't do any improvements? So we introduced in the last slide pipelining. This is for the stop and wait, to deal with that. But we're gonna look at a protocol that implements, pipelining is like go back and sender. So here what we have is that the sender can have a window of up to n. These are unacknowledged packets and flights. And let me show you a visualization that would be better. So the sender itself has a window and it has a window size of n. And each packet carries a specific sequence number with its header. In the diagram here, we have green has been already acknowledged. So that means it has been sent and received an acknowledgement for it. Yellow is it's sent but not yet acknowledged. And blue is it's usable and ready to be sent. And then we have white that are not yet usable because we're only dealing with the window size. So the window slides forward as more acknowledgements arrive. So it would move over here to the right as we get more green in. And the acknowledgements are going to be cumulative here. So it means all the packets up to sequence number n have been received. So when we receive an acknowledgement, it slides forward to n+1, the next packet over. So the window size would increase by 1. So here's that the two last bullet points is that the sender runs a timer for the oldest unacknowledged packet. And if the timer expires, the sender retransmits the packet, and all the packets that arrive in the window would go back and resend it. So that is for the sender. Just a recap again, we have a window size, and we have indicators that indicate to us what is being sent or not. The window size would increment by 1 after we receive 1 acknowledgement for the packet that we have sent. And we know if there's a loss or error or corruption, we already have dealt with that. We're just talking about the utilization and the pipelining here. So go back and here for the receiver. It is very much simpler than the sender. So the rule is that always acknowledge the highest in order packet that has received so far. So if an out of order packet arrives, the receiver we know would discard it, or it would not buffer it, it would not hold it in place, it would just neglect it. Or has the option to hold it. That's like the implementation choice. There could be a tweak to that. So either way, it will send an acknowledgement for the last order packet. So green is going to be received and acknowledged. Red is going to be out of order, received but not acknowledged. So in this implementation, it is holding it in the buffer, but is not neglecting it. And then we have our white that is not received. Here that we see at the bottom, RCV base, this one marks the last expected order of sequence number. So it just basically the base that we have for the receiver. So we have a base for the receiver and sender. So the receiver doesn't really need to track much. The sender is doing the tracking, but it is keeping track of what's coming and what has been sent back and acknowledged. Okay, let's go and just see how this works exactly back in action. And then maybe after the slide, we can stop. So we have a window size of 4. So we have a sender and receiver. So at time 0, the sender would transmit packet 0, 1, 2, and 3. And this run, packet 2 is being lost. On the receiver side, we have received packet 0, we send acknowledgement 0, we received packet 1, we send acknowledgement 1, and then packet 2 is lost. Packet 3 arrives out of order. And we know when something arrives out of order, we don't just send it back. It is discarded and it resends. We are waiting to resend acknowledgement 1. So acknowledgement 0 and 1 and duplicate 1 are now propagating from the receiver back to the sender. So now the window size would be increased. So the sender would receive acknowledgement 1 and or acknowledgement 0 here, sorry, and it would slide the window forward. This sends packet 4, but it's still being discarded because packet 2 has not been resolved yet. And also we receive an acknowledgement from packet 1, and then it would slide again to packet 5. The window side would increase, but it's also discarded again because we haven't dealt with packet 2 yet. So the sender now sees another duplicate acknowledgement. It just ignores it. There is no action that is really taken. So the receiver gets packet 4 and 5, and since packet 2 is still missing, both are discarded. The receiver keeps sending duplicate acknowledgement once, acknowledging the last order of packet that is successfully sent, which is packet 1. 1 successfully transferred over, but 2 has not. So eventually there's a timeout, and this is the use of the timeout, is that the sender time for packet 2 will expire, and the sender retransmits packet 2 because it's a go back and retransmits. So it goes back and retransmits 2 because it has been lost, and it retransmits 3 and 4 because they have been 3, 4, and 5 because they have been discarded. So it just sends it back again to the receiver, and the receiver would this time make sure that it is have successfully sent back to the sender. So that is the full go back in cycle. We see how packet loss leads to discarding out of order packets and retransmission of multiple packets. Okay, this is a good stopping point for us, I think. And we're going to talk about also an improvement. It's a selective repeat. So we will stop here. I hope that does the concept make sense so far what we are trying to build? Hopefully it does make sense. If there's something that you're unsure about, you can just reach out to me and I can clarify that more to you. But the idea is that we are trying to send data in a reliable order, and we have problems, and we are trying to deal with the problems by adding new features. So that is that. If you don't have any questions, you are free to go, and I'll see you on Monday. And I'll keep you updated about the midterm and all that stuff. Oh, thank you.